Okay, this is the recap for Lecture 5 of Formal Methods, and the topic today is Boolean operators. So let's take a look. The first operator that we're going to discuss is conjunction. The name of the operator is conjunction. The symbol is this, looks like a capital A without the little crossbar. That's a good way to remember it because the capital letter A is the first letter of and that's how you say it in English. So if P is a variable and Q is a variable, then P and Q is the way you say that, is the way you say conjunction. The individual P and the Q are called conjuncts. And the truth table is shown here. So here we have P and Q, the possible values of P and Q, there's 4 possible states. Remember what the state is? A list of variables and their values. So P is a variable and Q is a variable, and there's 4 possible states: true, 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 false, false, true, and false, false. And so the column on the right is the conjunction of those 2 variables, P and Q. And so if P is Q in the first row, if P is Q and true is true, then P and Q is true. If P is true and Q is false, then P and Q is false, and so on. And so we see that the only way that this table can be true, the only way the conjunct of 2 variables can be true, is if they are both true. An easy way to see that this is natural, this is a natural interpretation of the English expression, is to consider a sentence with the word and in it, the conjunct and, the conjunction and. Suppose we say that the sky is blue and the grass is green. Well, the sky is blue is obviously true, and the grass is green is obviously true. So when we say the sky is blue and the grass is green, the whole sentence, the sentence taken as a whole, is true. Now, if one or both of those is false, on the other hand, then the entire sentence is false. For example, if I say the sky is, well, I was going to say orange, but that can happen during a sunset. Let's say the sky is green and the lawn and the grass is green also. Well, the first statement is false and the second statement is true. So we see in the third row that the entire statement, the sky is, what did I say, green? The sky is green and the grass is green, is the entire statement is false. All right. The next operator is called disjunction, and the symbol is this upside down capital A, or it looks like a capital V, and the English expression is or. So when we say, the way we say that is P or Q, and P and Q, those are called disjuncts. So that's the terminology that we use for the part of an or expression. In the truth table, here again, there's 4 possible values for P and Q: true, 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 false, false, true, and false, false. And then P or Q is true if one or both of them are true. So if I say the sky is blue or the grass is green, both of those individually are true. So when we connect them when we connect them with an or, the entire statement, the sky is blue or the grass is green, is true. And the only way that it can be false is if they are both false. So if I say the sky is green or the grass is purple, then both of those individually are false, so the entire or statement is false. So that's the truth table for disjunction, pronounced or. Now the next one is implication, and this one always gives people problems when they see it for the first time. The operation is called implication. The symbol is this double-stemmed arrow pointing to the right. And the way you say it in English is P implies Q. There's actually 2 ways to say it. You can say either P implies Q, or another way to say it is if P then Q. So both words are common in English. Most logicians like to say implies. Other people, lay people like to say if P then Q. Now, each one of these P's and the P and the Q, they have different names depending on what side of the arrow they are on. In this, with implication, P is called the antecedent and Q is called the consequent. This is just logic jargon that we have to learn. We have to learn the vocabulary for logic. So P is called the antecedent and Q is called the consequent. So you can see why the Q is called the consequent, because in English you say if P then Q. So Q is what follows. It's the consequent. And P is called the antecedent. All right, so what is the truth table for if P then Q? Now, the example that I always give, and you can see this in the lecture, is I give this example. Like, if I win the lottery, then I'll buy a big red Corvette. And so P is this English statement, I win the lottery. Q is the consequent, is the statement, I will buy a big red Corvette, which is probably what I would do if I did win the lottery. And the only way that if P then Q can be false is if the antecedent is true and the consequent is false. That's the only way P implies Q can be false. So the only way that statement, if I win the lottery, then I will buy a big red Corvette, the only way that statement can be false is if I win the lottery and I don't buy a big red Corvette. That makes the statement, if I win the lottery, then I'll buy a big red Corvette, false. All other instances, the implication is true. And this seems a little counterintuitive when you see this for the first time. And the example that I give in class is, I drive up in a big red Corvette, and you say, did you win the lottery? And I say, no, I didn't win the lottery. So if I buy a big red Corvette, but I didn't win the lottery, that statement is still true. It's still true that if I win the lottery, then I will buy a big red Corvette. In other words, that scenario corresponds to the third row in the table, in the truth table. I don't win the lottery, but I buy a red Corvette. That does not negate the truth of the statement, if I win the lottery, then I will buy a big red Corvette. So you have to kind of think about that for a while. All right, and the next one is also implication, but it's the other way around. The arrow is pointing, instead of pointing from left to right, the arrow is pointing from right to left. Now the way you say this is follows from. So if you see in the truth table, you see P and the left arrow Q and the third column of the truth table. So the way we say this is P follows from Q. But another way to say it is if Q then P, because that's exactly what it is. It's just the same as implication, but it's written the other way around. Now it's important to understand that the antecedent, and which one is the antecedent and which one is the consequent. It's not that the antecedent is on the, it's not that one is on the left-hand side and the other one's on the right-hand side. It's which side of the stem of the arrow is it on. You see, in the truth table of P follows from Q, you see Q is, P is on the pointy, is the pointy end, and Q is the other end. Q is the tail of the arrow, and P is at the tip of the arrow, of the implication arrow. And so in this case, even though Q is on the right-hand side, Q is the antecedent and P is the consequent. All right, so you just have to keep that terminology in mind. You know, this is analogous to less than. Like if you say A is less than B, another way of saying that is B is greater than A. And it's the same thing. It depends on what side of the operator whether it's on the pointy end or the open end of the less than operator. All right, so now the third operator is called equivalence. Now equivalence is this, it looks kind of like an equals but with an extra dash. The symbol is this 3- symbol, and the way this is pronounced is equivales. Now this is kind of this was kind of promoted by this particular textbook that we're using, and I like the terminology that they use when they present this logic system. By the way, this logic system is called calculation logic. And so the way you say this in English is P equivales Q. Now there's a close relationship between equivales and equals that we're going to explore in a minute. So another way to say this is P equals Q, because equals and the equals operator has the same truth table as the equivales operator. So another way to say this is P equals Q. They are synonymous. They have some similarities, but then they have differences as well. But the truth tables are one instance that they are the same. They have the same truth table. All right, so the truth table, what is the truth table for equivals? Well, P equivals Q is true if and only if they are the same. So if P and Q are both true, then true equivals true is true. But they're also, P equivals Q is also true if both of them are false. So you see the last row, if P is false and Q is false, then P equivals Q is true because they're the same. So when are they not equivalent? When do they not equivalent each other? When they are different. So you see if P is true and Q is false, then P equivals Q is false. And if P is false and Q is true, then also P equivals Q is false. So that's the truth table for the equivalence operator. And we have an inequivalence operator, which is the equivalence operator with a slash through it. Okay, so in English we would say P, this is called the exclusive OR operator. So P exclusive OR Q. And another way to say it is P is different from Q. And basically what it is it's the opposite of P equivals Q. So if P equivals Q is true, P exclusive OR Q is false, and vice versa. If P equivals Q is false, then P exclusive OR Q is true. So you see that whereas the third column of the equivalence table is true, false, false, true, the third column of the inequivalence operator is false, true, true, false. So that's the inequivalence operator. And we have one, by the way, all of those operators that we looked at were binary infix. So negation is a unary prefix operator, and the symbol, we mentioned this before in one of our lectures. The symbol is this dash with a little hook on the end of it, this little hook that goes down, and the way you say that is not P. So because it's unary, then it's not in between two operators. So we just have one variable P, and if P is true, then not P is false, and if P is false, then not P is true. So these common English words, and, or, and not, are the basis of all these logic operators. But what we are doing is we are systematizing the way we normally think in English. We're just systematizing things that we should kind of have an intuitive feel for in the first place. Okay, so now what happens if you have a more complicated Boolean expression that has combinations of and, or, and not? So let's take a look at this table. This is right out of the book, the textbook. So the expression on the third column on the right it has P or parentheses Q and not R close parentheses. And the question is, what is the truth table for this entire expression? Now you see in this case we have three Boolean operators, P, Q, and R. So what's the definition of state? A list of variables and their values. So what is a truth table? A truth table is simply the value of the expression for all possible states that the expression can be in. So and by the way, I failed to mention that in Boolean algebra there are two constants. Do you remember the definition of an expression? The first part of the definition of an expression is either a constant or a variable. The constants in Boolean algebra are true and false. Okay, so if there are three variables, P, Q, and R, then there are 8 possible states. P, Q, and R can either be true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, or false, false, false. And so the way you calculate, this is called calculation logic. The way you calculate the truth table for a complicated expression is you just do each one individually, and you just build up as you go. So the first column on the right part of the table is not R. So you see what you do is you take the column for R, which is true, false, true, false, true, false, true, false, and you negate it. Well, if you negate that, what do you get? Can you anticipate what you would get? Wouldn't it be this? false, true, false, true, false, true, false, true. Are you with me? Now, how do you do the next column, Q and not R? Well, what you have to do is you take the column for Q, and you take the column for not R, and you AND them. Now, what's the rule for AND? They both have to be true in order to be true. So can you anticipate what the column for Q and not R here? Pause for a minute and see if you can figure out what this next column is. Okay, you should have gotten this. False, true, false, 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 true, false, false. Right? So you see that if you just run your finger down the column for Q and the column for not R, and you AND those. And then the way you get the last column is we have Q and not R, so you OR that with P. So you take the column for P and you OR that with the column for Q and not R. So see if you can do that. Okay, you should have gotten true, 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 false, true, false, false. So if either one or both are true, then it's true, but if they are both false, like on the, what is it, the fifth row, I think, P is false and Q and not R is false, and so therefore P or the quantity Q and not R is false in that case, and same for the penultimate and the last row as well. And here we have the table of precedence, and this is in the theorem sheet, the theorem document, and it's also in the inside front cover of your book, of the textbook, that discusses the precedence of each one of these operators. And notice the main thing to notice here is row K, and or. Actually, they have it in the opposite order there, or and have the same precedence. And so we have to make sure that when we have to make sure that we use the precedence table when we evaluate these Boolean expressions. And the thing that we just noted on that table is that and or have the same precedence. That means that when they are together, parentheses are necessary. Now I know the book has a rule to disambiguate this, but we're going to ignore that rule, and we're going to say that if you have and or together, the parentheses are necessary. Here's an example. If you say P and Q or R, I'm going to mark that as incorrect, okay? Because parentheses are necessary. So what are the two possibilities for putting the parentheses around these expressions? You can either put them around the first two, parentheses P and Q, close paren, or R. Or you can say P and parentheses Q or R, and those they have different truth tables. You can work that out if you want to see that those truth tables are different. But so when you have and nor together, I insist that you put parentheses around to disambiguate the expression. Okay, now I mentioned a minute ago that equality and equivalence have some things in common, but they have some things that are different. There are some properties of them that are different, and we need to explore this in detail. This is going to come up again and again, and this is when students first learn about equivalence, they have a misconception. They attribute attributes of equivalence from equality that's not the case. So let's explore the properties of equivalence versus equality. First of all, as I mentioned before, equals and equivales have the same truth tables. Okay, so that's just a fact. And so the truth table we showed the truth table for equivalence, that's the same truth table as for equals. But there are four differences, okay, and here they are. First of all, equals is for numbers and Booleans. I could have said and sets and lots of other things, anything. All right, so equals is for numbers and Booleans. On the other hand, equivales is only for Booleans. So it doesn't make sense to say x equivales y when x and y are integers. That would be incorrect. You would have to say x equals y, not equivales. Okay. So number one, equals is for numbers and Booleans. Equivales is only for Booleans. Second difference. Equals has higher precedence than equivalence. Let's check out the table of precedence to see where they are. Okay, so here's the table of precedence, and we see that you see row M at the very bottom, that's equivalence, that has the lowest precedence. But where's the equals? It's up on row J, together with the less than and the greater than symbol. All right. So equals has higher precedence than equivalence. So that's one difference. That's another difference. Okay. Okay, so back to our slide. Equals has higher precedence than equivalence. And for example, you don't need parentheses for this expression. Now let's take a look at this expression. You see x times, well, first of all, multiply. Let's look at the x times y equals 0. First of all, multiply has higher precedence than equals. So x times, you do x times y first, and then you see if that, and then you see if that equals 0. So that's one expression. And then on the right hand side of the equivalence, we have x equals 0 or y equals 0. So notice that this does not mean that x times y equals 0 equals x equals 0 parentheses and then or y equals 0. So you see, you do the equals first and then you do the equivalence. So, and I've indicated that by the spacing. You know, there's a little extra space on either side of the equivalence to show that you do everything on the left of the equivalence, and you see whether or not that is equivalence to everything on the right of the equivalence symbol. So, and we're not going to talk about types very much until a bit later when we get to predicate calculus. But you should be aware of the types of this. So if x is a number and y is a number, then x times y is a number. 0 is also a number. Let's assume that they are integers. So either x times y is equal to 0 or it's not. So you see that x times y equals 0, that's a Boolean expression. That's either true or false. All right? And then x equals 0 or y equals 0. On the right-hand side of the equivalence, each x equals 0 is a Boolean, and y equals 0 is a Boolean, and or is a Boolean operator. So the x equals 0 or y equals 0 is a Boolean operator. So you see that the expression on the left of the equivalence is a Boolean expression, as is the expression on the right-hand side of the equivalence. All right, third difference. And this is what's tricky. This is what students have a hard time grasping with equivalence. Equals is conjunctional, while equivalence is not. Now here's what we mean by conjunctional. And this is super important, and I can't stress how important it is that you get this concept under your belt right now. When you say in English, or in algebra rather, when you say in algebra, B equals C equals D, this is very common notation in algebra. What does that mean? It literally means, formally, it means B equals C and C equals D. Now, usually when I ask students, what does B equals C equals D mean? They say, well, it means that B equals C and B equals D. That's a consequent of what it means, but that's not literally what it means. What it means is B equals C and C equals D. All right? Now, and I'll give an example of this in a minute. And so, if equivalence is not conjunctional, what is it? Equivalence is associative, while equals is not. So, what does associative mean? Associative means that it doesn't matter where you put the parentheses. If you have B equals C equals D, you can put the parentheses around the B equals C, or you can put the parentheses around the C equals D. In other words, when you evaluate the truth table for B equals C equals D, it doesn't matter whether you do the B equals C first and then equal that to D, or you do the C equals D first and then you do B equals that. Those are equivalent. That property is called the associative property of equivalence. And the important thing is that, and students always frequently get this wrong, equivalence is not conjunctional. And we will see examples of this, many examples of this, when we start getting into the proofs themselves. All right, so let's take a look at an example of equality versus equivalence. Now, let's consider the state. Now, what is the definition of state? List of variables and their values. So let's suppose we have three variables, B, C, and D. And let's suppose that they are in the state B is false, C is false, and D is true. And let's explore equivalence versus equivals. Now, first let's consider B equivals C equivals, parentheses B equivals C, close paren, equivals D. Let's consider this Boolean expression, all right? And let's consider that it's in the state B is false, C is false, and D is true. Then what we would have is B is false, C is false, open paren, close paren, equivals, D is true. So now, because we have the parentheses around the first, what is false equivals false? Do you remember what that would be from the equivals truth table? Okay, that's true, right? False equals false, equivals false is true. And then true equivals true, what is that? Well, they are the same, so that is true. All right, are you with me? Now let's put the parentheses around the C equivals D. So now let's evaluate B equivals parentheses C equivals D. Now, if B is false and C is false and D is true, then that computation is in this state. That Boolean expression is in this state. False equivals parentheses false equivals true. Now what is false? But now this time the parentheses is around the C equivals D. So what is false equivals true? What is that? Do you remember that from the truth table? Isn't that false? So what we have then is false equivals false. But what is false equivals false? That is what? That is true. All right. So now what do we notice? What do we notice about whether we put the parentheses around the first pair or the second pair? We notice that they are the same. All right. And you can work it out. You can work out the truth tables for all 8 possible states. You know, true, 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 false, true, false, true, true, false, false, etc. And you will get the same answer regardless of whether you put the parentheses around the first pair or the second pair. Now, so you see, this is an illustration, an example of the fact that equivals is associative. But now look, that's not the same thing as equals. If you say B equals C equals D, all right, what is the conjunctive meaning of B? You cannot put the parentheses around the B equals C, and you cannot or put the parentheses around the C equals D, because equals is not associative. It is conjunctive. So what is the conjunctive meaning of B equals C equals D? It's B equals C and C equals D. So now let's work this one out. So if we are in the state B false, C false, D true, what do we have here? We have the expression false equals false and false equals true. Now what is false equals false? Remember, the same truth table applies. So false equals false is what? That's true, right? And false equals true, that's what? That's false, right? So we have true and false. But now what is true and false? That is what? That's false. And that's not the same as if it were associative. So that's an example to show that that associativity and conjunctivity are different. And that's the end of our recap. See you next time.